Good morning. I'm Gokul Swami, and I'm a senior machine learning scientist with Amazon. I take this opportunity to welcome you to this session on Introduction to Probabilistic Graphical Models. This will be a two-part session, with the first part covering the basics and a second part involving more advanced concepts. Moving on, we will start off with a basic introduction to probabilistic graphical models along with some real-world applications. We will then move on to discuss directed graphical models and Bayesian networks. Following this, we will touch upon undirected graphical models, factor graph, and also discuss this in the context of Markov networks. Subsequently, we will discuss how to do parameter estimation in graphical models and also discuss the inferencing problem. We will close out the first part with a discussion on why inferencing is hard. And in part two, we will continue the discussion on what methodologies can be employed to make inferencing practical for real-world problems. So an example of a graph network is shown in this slide. So A, B, and C are three nodes, and the red arrows are the edges that link the vertices. The nodes ideally represent random variables, and the edges encode the relationship between these random variables. Also, as you can infer from the graph, the arrows are directed from one vertex to another. So this essentially encodes the directional or causal relationship between the node entities. As an example, consider a graph which comprises of nodes which are essentially diseases and symptoms. So you would expect the arrows to flow from the disease towards the symptoms, because ideally a disease can cause symptoms, but not the other way around. So such graphs are often referred to as directed graphs. In certain instances, no such causal relationship might exist, and in such cases, the graph is said to be undirected. As an example, consider a graph comprising of people shaking hands at a party, wherein the nodes are the people, and an edge represents if any two people shook hands. In this case, the graph is undirected, as no directional relationship can be established. I mean, shaking hands is kind of a very mutual thing, and there's no directionality associated with it. So in the next few slides, we will see several examples of graph networks in real-world scenarios. Before I proceed further, I would like to kind of state that it is assumed that the audience is familiar with basic concepts in probability to be able to grasp the contents of this lecture. Okay, the first application we pick up is spam filtering, right? So in this graph, spam is a random variable that takes on two values, 0 or 1. W1, W2 up to Wn are words that are drawn from, let's say, a finite dictionary and are essentially dependent on what is the value of spam, the spam feature. So we use the word dependent a little informally here, but to make it more formal, we can view the graph as a generative model where the value of spam dictates what kind of words W1 to Wn are likely to be. So let's say if spam is equal to 1, then the conditional probability of words such as lottery, offer, exclusive, which we quite often associate with spam, would have a fairly high probability of occurrence. So another interesting aspect of the graphical model is that given the spam nodes, the words W1 to Wn are independent of each other. And this is often referred to as conditional independence. So conditional independence is a fairly important concept that will be occurring several times in this lecture. So conditional independence allows us to factorize the probability distribution as shown in the expression below. So the expression here. In a real world scenario, the words W1 to Wn in a sentence, right? If you look at, let's say, an email sentence, are unlikely to be independent of each other because there is a certain structure associated with the language. But in many cases, in real world, even for real world problems, you make simplifying assumptions like the one we have made here, saying that given spam, the words are independent, to be able to arrive at a feasible probability distribution that can be computed. Right, so and we do this often to make machine learning and inferencing easier. So moving on, Now we kind of give out more examples of what kind of real world graphical models do exist. So here is one such example. So we look at a graph of diseases versus symptoms. So as expected, the graph is directed with edges originating from the disease node and going to the symptom node. The symptom node is the one at the bottom here, right? Indicating what symptoms are caused by any given disease. So using this graph, let's say a learned graph, and given a list of symptoms, we would then be able to infer what is the most likely disease that is causing all the symptoms. So this is one example of how graphical models can be employed in practice. So another example is from natural language processing, where we use a hidden Markov model to assign parts of speech tags such as noun, pronoun, etc. to the words in a sentence. So this can be very useful for a host of applications such as information retrieval, text-to-speech, etc. So in fact, Amazon Alexa is one very good example where you can use a network of this type to do text-to-speech synthesis. Graphical models are also very useful in vision tasks, wherein, for example, in the picture on the left, we can think of each pixel as an observed node represented by blue circles. The observed nodes are in turn connected to hidden nodes represented by red circles, which encode more semantically useful information, such as whether the given pixel corresponds to the, let's say, animal class or sky, grass, etc. So once again, given the hidden node, the observed pixels are independent of each other. The hidden nodes, in turn, are connected to their immediate neighbors, representing the fact that neighboring pixels have a very high likelihood of belonging to the same class, unless there is a strong evidence to the contrary. A graph of this nature can be used, for example, to perform image segmentation with a certain number of classes. So with this last example, we will move on to discuss the mathematical underpinnings of directed acyclic graphical models, or DAGs, which are also often referred to as Bayesian networks. So to understand directed graphical models in a little more detail, we will make use of the canonical student network example that is shown on this slide. So this network has 5 different nodes: difficulty, intelligence, grade, letter, and SAT. So difficulty signifies how difficult a given test was, with 0.6 indicating that the test was not difficult, and 0.4 indicating that the test was difficult. Right? Intelligence signifies how intelligent the student is, with a 0.7 probability the student is not intelligent, and a 0.3 probability the student is intelligent. Grade essentially has 3 levels: 1, 2, and 3, with 1 indicating a good grade, 2 indicating a medium grade, and 3 indicating a poor grade. Grade here essentially depends on the difficulty of the exam and also how intelligent the student was. Then there is letter, which depends on grade. So letter here signifies, let's say, a letter of recommendation, and it obviously must depend on grade, because if you get a good grade, then it is very likely that your professor will write you a good letter of recommendation. Finally, SAT is, let's say, a score on an external test like JE, for instance, and has 2 levels, S0 and S1, with S0 indicating a poor SAT score and S1 indicating a good SAT score. Now, SAT here essentially depends only on intelligence of the student, as to how intelligent the student is. Okay. So the table next to these nodes kind of encode the probability or the conditional probability distributions of those node features, right? So here, if you look at difficulty, you have 2 levels of difficulty, D0 and D1, and the numbers there, 0.6 and 0.4, correspond to the probabilities associated with those difficulty levels. Since difficulty does not really depend on any other node, right? It's an independent random variable in that sense. And so therefore, there is no conditional aspect to difficulty. The same applies for intelligence. So intelligence, essentially, there is no other variable or node which influences intelligence, and therefore there is no conditional aspect to intelligence as well. So moving on, now if you look at the SAT variable, right, or SAT node, things become a little more interesting. SAT now depends on the intelligence of the student. Intuitively, you would expect if a student is intelligent, then his SAT score would be high. Whereas if a student is not intelligent, then his SAT score would be on the lower side, right? So now since SAT essentially depends on intelligence, we will now, to enumerate the probability distribution of SAT, we will have to enumerate it for all possible values of intelligence. So that is what is shown in this particular table here, wherein you have the probability distribution conditioned over two different values of intelligence, with I0 being intelligence of 0, that is low intelligence, and I1 being high intelligence. So in the case of low intelligence, you can see that the intersection of I0 and S0, the probability value there is 0.95. So what this essentially signifies is that if the student is not very intelligent, then what is the probability that his SAT score would be low? And that is fairly high, which is equal to 0.95. And again, this is kind of makes sense because like we discussed earlier, a student with a lower intelligence is likely to do poorly on this particular test. On the contrary, if you look at the case where let's say the student is intelligent, but his SAT score is still poor, which is S0, intersection of I1 and S0, you can again find the probability value there to be 0.2. So here again, this makes a lot of intuitive sense because if the student is intelligent, then there should be a lower probability of him doing poorly on this test, right? So this is how you would essentially encode the conditional distribution of SAT given the intelligence feature, right? Or given the intelligence node. And this is a very, very important aspect in Bayesian networks. So finally, we look at the node associated with the grade, right? Like I had mentioned earlier, the grade has three different levels, 1, 2, and 3, with the 1 signifying a good grade, 2 signifying a medium grade, and 3 signifying a poor grade. Now, interestingly, grade depends on both the difficulty as well as the intelligence, right? So now when you start enumerating the conditional distribution of grade, you will have to account for all possible combinations of difficulty and intelligence. Now, difficulty takes on two possible values, intelligence takes on two possible values. So therefore, the total number of enumerations in this particular case happens to be 4. And that is I0 D0, I0 D1, I1 D0, and I1 D1, right? And that is essentially what is shown in the table next to the grade node. So, so again, to take an intuitive example, the question, let's say, if you can read off this table, what you would likely to be infer is that what is the probability of the grade being poor, which is G1, given that the student is not intelligent, as well as a test is not difficult. In this case, it happens to be 0.3. Right. So in a similar fashion, you can kind of take another example wherein you can ask the question, what is the probability that the student gets a poor grade when the test is difficult, as well as the student is not intelligent? So if you look at this table, you will find the corresponding value to be 0.05. And this makes a lot of sense because if the test is difficult as well as student is not intelligent, then you would expect this value to be fairly small. Now the question is, how did you even get these numbers? How did you fill up this table? Right? These numbers don't appear magically. They are learned as part of the parameter estimation process that we will discuss in the later portions of this particular lecture. But what this graph does do is to lend a particular structure to the probability distribution or the joint distribution of all these features, as we will see in the next slide. So we are ultimately interested in characterizing the joint distribution because, as we will see later, having the joint distribution lets us characterize any marginal or conditional distribution that we may be interested in. So typically, let's say if we had some kind of a magic wand that gave us the joint distribution, then we would be sorted for, in all practical purposes. But for most cases, it is next to impossible to characterize a joint distribution without assuming some kind of relational structure. So the Bayesian network we have been discussing so far helps us break down the joint distribution into manageable chunks, if you will. And this makes it much more simpler to learn the network parameters. So the one way we would essentially construct a joint distribution, but before I go into that, just a note on what a joint distribution essentially implies is essentially the probability of co-occurrence of all the features. That is probability of D, I, G, S, L. That essentially is what constitutes a joint distribution in probabilistic parlance. Now, given this graph structure, how would you break down this this joint distribution? So let's start with the letter, right? Letter node. We can see that the letter node depends on the grade. So we write down the first expression or the conditional expression, which is the joint distribution equals to the probability of letter given grade, right? And that's the first term that you see on the right on the equation that is shown in white on this particular slide. So now that we are done with letter, let's move on to the node grade, right? Now, as we can see, the grade essentially depends on the difficulty and the intelligence, right? So then how would we, the way we would write down the conditional distribution in this particular case would be probability of grade given difficulty, intelligence. And that is what is shown as the second term on the right of that particular equation. And then moving further up, let's say we hit the difficulty node. We can see that nothing really influences difficulty. While difficulty influences the grade really does not influence difficulty. So the difficulty in some sense is an independent node or independent feature. So we just take the probability of difficulty and multiply it with the expression that we have gotten so far. And then the same story applies for intelligence. So you end up with multiplying probability of I to whatever whatever the product you had up till now, right? And then finally, let's look at the SAT node. Clearly, the SAT only depends on the intelligence, right? So, so if you were to write down the conditional expression for this particular case, you would write probability of S given I, where I is the intelligence. So this is how you would essentially break down, let's say, what would have been a complex probability distribution into a much simpler expression based on conditional distributions that arise out of this particular graph structure. So I hope the way we have broken down this joint distribution is clear, because that essentially forms the crux of the Bayesian network, and it makes both parameter estimation as well as inferencing, a much simpler task than it would have been otherwise. Yeah, okay, so far we have discussed the directedness property of Bayesian networks, but there's one particular aspect that we haven't really paid much attention to, is essentially what is known as acyclic or the acyclicity. So I think I kind of previously mentioned that Bayesian network essentially is a directed acyclic graph. So we already know what directed is, but let's pay a little more attention to what is probably meant by acyclic, or what the acyclic property is. Take a look at this graph on this particular page, right? And it has three nodes, A, B, and C. And there are arrows or edges that emanate from this node and are directional and end on some target node, right? There's a node that goes from A to B, and B to C, and C to A. Now, a graph is said to be cyclic if you can start at a particular node, follow the directional edges, and arrive back at the same node, right? In this case, there is such a path from A to B, B to C, and then from C to A. So this graph essentially has a cycle in it, or it's a cyclic graph, right? Now, why can't we have cycles in our graph? What essentially is the problem there? So now let's look at a simple characterization of the nodes or the probability distribution at the nodes. So now you can see that the node A depends on the node C. So therefore, if you were to write down the conditional distribution of A, you would enumerate it based on the different possibilities of C, which being C0 and C1. And so we have taken a particular example where A0, or a value probability of A taking on a value of 0, when C is 0 is equal to 1, and the probability of A taking on a value of 1 when C is 0 is equal to 0. And in a similar fashion, if you look at the node B, based on the direction of the arrow, you can infer that the node B depends on the value or the feature corresponding to the node A. So once again, you can kind of enumerate the probability conditional distribution of B given the two possible choices of A. And in a similar vein, you can do it for the node C as well. Now, if you were to essentially estimate the joint distribution based on this network and estimate the joint distribution for, let's say, a particular case where A equal to 0, B equal to 0, and C equal to 0, you would essentially end up with an expression like this, right? So you would split the joint distribution as probability of A equal to 0 given C equal to 0 times probability of B equal to 0 given A equal to 0 and probability of C equal to 0 given B equal to 0, right? This is something that we have learned as to the process that we followed for the student network example as well. So if you actually plug in the values, you will find that this probability actually tends to be equal to 1. Now, let's look at another example where A equal to 1, B equal to 1, and C equal to 1, and we are interested in characterizing the joint distribution of this particular feature set. So once again, if you expand it, you will find you follow a similar process wherein you have probability of A equal to 1 given C equal to 1 times probability of B equal to 1 given A equal to 1, because the node B only depends on the value of node A, and then probability of C equal to 1 given B equal to 1. And if you plug in the values, you once again find that this probability happens to be 1. Now, this is a major contradiction, right? Because you cannot have two different probability values being equal to 1. It kind of violates the basic concept that the probabilities have to sum to 1. And this is one of the reasons why having cycles in your graph essentially makes it fairly difficult or even impossible to properly assign properly get a proper representation of conditional distributions. So Bayesian networks essentially must be acyclic in order to guarantee that their underlying joint distribution sums to 1 and it is properly normalized. Okay, so I'm going to take a brief diversion here. So while we mostly remain focused on directed graphical models and Bayesian networks, I'm going to touch upon undirected graphs in this particular slide. So as mentioned earlier, undirected graphs result from situations where a clear causal relationship cannot be established between the nodes. For example, in the image on the left is tiled into m cross n nodes, with each node connected to 4 of its neighbors with no directionality inherent. Here, instead of dealing with conditional distributions, we will make use of potential functions, the chi of C, which are defined over a clique. So clique is nothing but a set of nodes that are connected to each other. So in this particular example, a clique is formed by any set of two nodes which are adjacent to each other, right? The joint distribution then effectively factorizes over all possible maximal cliques, as shown in the equation on the slide, with Z indicating a normalizing factor to ensure the distribution sums to 1. The potential functions are something we define, such as let's say the exponential functions or any other function suitable for our particular purpose. The graphs resulting from such a presentation are also often referred to as factor graphs, because these the terms in the product essentially are some kind of factors, which essentially get multiplied to construct the joint distribution. So there are many examples of undirected graphical models, such as conditional random fields, which I am guessing that you would have probably learned about in another lecture. But however, for this particular lecture, we will mostly remain focused on directed models and not discuss too much of undirected graphs. So I encourage you to kind of go back and study, and go dig deeper into undirected graphs and see how they are very closely related to what we are studying in terms of directional graphs and Bayesian networks. Okay, so we did post this question earlier in terms of how did we essentially get those values in that student network? How do we know what those probability values are? right? So typically there are multiple scenarios. One is, let's say you have an expert on your side who sits and fills out that table for you, right? He has a lot of domain knowledge. He understands the problem in and out, and is sitting there and filling out all those values for you, which essentially make a lot of intuitive sense, like we did for the student example. Um, but for a large majority of problems, you would really not have an expert who can do that for you, or the problem scale itself would be so large that it becomes infeasible for an expert to really, start filling out the probability tables, given the number of enumerations that would result from a large graph, right? So how exactly then can you go about in a principled way to establish, so to estimate those parameters? So let's motivate this with a simple example of, let's say, a graph with a single node and no edges. So since this graph, this is also a very simplistic example of a Bayesian network. So here, let the probability of, so this graph, this node, particular node, let's say is the coin toss, right? Where the probability of heads is represented by a theta, and the probability of tails is 1 minus theta, right? So now how would you really estimate this particular theta? Theta is the parameter here of interest that we are yet unaware of and you would like to estimate. So this is fairly straightforward. You would cost the coin n times, okay? And then in those n trials, you would perhaps notice that there are n h times heads occurring and nt times tails occurring. So then what you would do is you would essentially construct a likelihood in this particular form, theta times theta to the power nh into 1 minus theta to the power n of t, nt, sorry, and then take the log of this to arrive at an expression of this form. And then if you actually differentiate this with respect to theta and set it to 0, you would end up with this particular expression, right? Which is very intuitive. I mean, the probability of heads is the number of heads given by the total number of trials. So this is essentially a maximum likelihood estimate. Let's say if this particular equation, the log likelihood, was very complex, in which case it doesn't really allow you to compute a gradient and set it to 0 and solve for it analytically, then you would end up using the workhorse of machine learning, which is the gradient descent, to solve for this particular parameter estimate. So both of these methods, the analytical solution as well as the gradient descent procedure, would help you converge towards the optimal theta, which in this case is referred to as the maximum likelihood estimate. So while we have done this for a very, very simple graph, which is a single node coin toss example, you can extend it to any kind of network. So the same concepts would apply to the student network as well, wherein all those values that we saw on this probability table there would then become parameters. And then based on the number of training samples that you see, for example, one training sample, you would have a particular difficulty, grade, letter, SAT, and intelligence. And for some other sample, those values would be different. You take all these training samples, form the likelihood expression, and then apply gradient descent to find to fill those values in those probability table, or find the values of those parameters in those probability tables. So in that sense, nothing changes from this very simple example to the student network. And the same can also be extended to even more complex networks, because it's a very well established and a straightforward method to do parameter estimation. Okay. So given a parameter set, right? Like I said, let's say you have a training example wherein you have the grade, letter, intelligence, SAT, and so on. You would be able to construct a likelihood for that particular training example, right? Given the set of parameters. But then what happens if, let's say, one of those parameters, one of those features are missing? For example, let's say a teacher was making recorded all these values for a particular student, but for some reason forgot to include the grade in the recording. So in this case, the grade becomes a missing feature. So such cases are far too common in real world examples, and therefore we need to deliberate on an approach to solve for it. So one very potent algorithm that can handle such cases is the expectation maximization algorithm. So here we assume that the missing features are characterized by a latent vector z, and then we first compute the probability of z given the x and the current estimate of theta. Theta is our entire parameter set. So once we have this distribution, we compute a weighted likelihood or the expectation, of probability of x comma z given theta dash under the distribution of z given x comma theta, and then re-estimate a theta dash that maximizes this particular likelihood, right? So this process is continued in an iterative fashion until convergence. So so to get an intuitive understanding of what is happening, let's take a simple example of, let's say, given x and the current estimate of theta, you are somehow able to estimate z or the missing features very accurately, right? In that case, the probability of z given x comma theta would tend towards a delta function, because you know exactly what the value of z is going to be, because given the x and theta, you have very good knowledge of what those missing features values are. Then what you do is, in that case, if you look at the m step, so what happens to the expectation there, right? So if you take the expectation of z given x comma theta, since p of z given x comma theta is a delta function, so the expectation essentially vanishes, and you only are, so what essentially then happens is that you substitute the value of the very confident estimate of z that you have back into this expression for likelihood. You fill in the missing features, and then you kind of use gradient descent on that particular likelihood to estimate a better theta or theta dash, right? So in a general scenario, what would really happen is that you would not be able to very accurately identify what those missing feature values are likely to be. In that case, you will end up with, let's say, a probability distribution of z given x and the current estimate of theta. And then what you're essentially doing is that you're plugging those values of z back into your likelihood expression, but also weighting it by the probability of that z occurring given the current given the observed features x and the current estimate of theta, right? And then you do this in an iterative fashion. For example, you get a better theta dash, and then you go and get a better estimate of z, and then you come back and get a better estimate of theta dash, and then you do this in an iterative fashion until you get a good you get a good solution wherein the parameters have converged and you are able to address this missing features problem very effectively. So, so this is a very simplistic, over-the-top explanation of what expectation maximization is trying to do. So we have, of course, glossed over many of the mathematical underpinnings of EM, and to be honest, an entire lecture can be devoted on this topic. But I don't think we will have the time to go into those kind of details in this particular lecture. Okay, so we discussed maximum likelihood estimation. But then is maximum likelihood estimation suitable for all practical purposes or all problems? The answer apparently is a no. So let's take a simple example. Once again, we go back to the coin toss problem. So let's say somebody wants to estimate the probability of heads. So this person went and tossed the coin twice, and in both cases, it resulted in a heads. Now, if we use the Emily estimate for P, which was the number of heads divided by number of trials, you will get 2 divided by 2, which is equal to 1, right? So, so then the person will conclude that the probability of tails occurring is 0. Is this so? This of course is grossly incorrect, right? So, so even a lay person would be able to tell you that, hey, you haven't really conducted sufficient trials for you to be able to get the accurate probability in this particular instance. So if you take a counter, if you, let's say, observe 400 heads and 600 tosses, then you're way more confident of your estimate of probability of heads compared to, let's say, conducting just 2 trials. So what is the so what really is the problem here? The problem is that the maximum likelihood estimation does not incorporate any notion of confidence in our estimates. And that can prove problematic, especially in scenarios where your data set is limited. And let's say even in scenarios where you're learning a large set of parameters, but you really don't have sufficient data to be able to characterize them very effectively. So then what is the workaround for this? So what we need to do then is to move away from this maximum likelihood estimation concept and start looking at the problem from a Bayesian statistical viewpoint. Okay, so so what exactly is Bayesian modeling? So sorry. So when we are doing likelihood estimation, what we essentially end up doing is we take the data and we take the probability of the data under a given, let's say probability of X given theta, or the probability of data under the parameter set that we're trying to estimate, and then try to maximize it to get the most optimal value of theta. That is your bare basics likelihood estimation. But in general, if you look at that is from a Bayesian perspective, why should theta be a point estimate? Theta itself can be a distribution, right? So let's say if you look at the distribution of theta, given the data that you have collected, that is P of theta given X, you can split it using the Bayes theorem in this particular fashion, where probability of theta given X is equal to probability of X given theta into P theta divided by P of X. So now you can see that basis this particular expression, P of theta given X is no longer a point estimate, but it's a distribution, right? And this, so what is the benefit of doing this is that if you're able to estimate a distribution for theta, you are able to get a very accurate sense of how confident you are in your estimate of theta, and that is what is very important in terms of constructing this Bayesian modeling. Well, one problem with estimating this distribution is that you have a P of X appearing in the denominator there, which is the probability of the joint distribution of the data, right? But that is not easy to estimate. In most real world examples, it'll be practically impossible to estimate this particular distribution, which is P of X, right? So then what we can do is, since P of X does not explicitly depend on theta, we can remove it from the expression and put a proportionality constant there. That P of theta given X is proportional to P of X given theta into P of theta. Now it's interesting to see the two terms on the right here. The first term, as we talked about earlier, the probability of the data given the current, given the estimate of the parameters theta, is nothing but the likelihood, right? And in MLE, what you would essentially do is go ahead and maximize its likelihood to find the best possible theta. But then you also have another term sticking to the right, which is P of theta, right? So this term is the prior, wherein you encode some prior knowledge about your about your estimate of theta, right? This prior knowledge could be as simple as saying that, hey, I believe theta to be a uniform distribution, or it could be a Gaussian distribution, or a beta distribution, or whatever it is. You have some idea of what theta should look like, and then you can encode that into your prior. And then what you do is you can go ahead and maximize this particular expression, that is P of theta given X, which is called the posterior, and arrive at an estimate which is known as the maximum a posteriori estimate, or commonly known as mapped estimate. Okay, so let's take an example once again. How would you do this for a simple coin toss problem? Right, once again, P, let's say, is a probability of heads, right? Where and xi is a random variable that you observe. Let's say you do n trials, x1 to xn, where xi equal to 1 if the ith trial resulted in a head, and xi is equal to 0 if the ith trial resulted in a tail. So then how would you essentially construct the likelihood for this function? Likelihood for this would be likelihood given theta, that is P of X given theta, in this case would be this particular expression here, right? So P of Xi times 1 minus P into 1 minus Xi. So when Xi equal to 1, or you observe a heads, then the likelihood for that particular training example is P. Whereas if you observe a tail, which is Xi equal to 0, then the likelihood happens to be 1 minus P, right? Which is very, very, very straightforward. Now, apart from this, we also do one more thing. We assume a prior on P. So now P is no longer a number, but let's say we characterize P by a distribution, right? And in this case, P happens to be a joint a beta distribution, right? So we have assumed P to be take the particular form of a beta distribution characterized by the two parameters A and B. So why a beta distribution? So that's again is a fairly interesting question, and one that we will try to answer in the next slide. So typically, the prior is chosen such that it satisfies what is known as the conjugacy property. So by choosing a conjugate prior, right, we ensure the posterior distribution. Remember, we had discussed the posterior distribution earlier, which is the likelihood times the prior. So if you choose a conjugate prior where p theta becomes a conjugate prior, then what happens is the posterior distribution ends up having the same form as the prior distribution. So this has huge ramifications when performing variational inferencing, as we will see in the second part of this particular lecture. So for the coin toss problem, once again, we assume P to follow a beta distribution, which is characterized, basis this expression here. And then recall that we have the likelihood, which is given by this particular expression for the, let's say, likelihood for the ith trial. So then to compute the posterior, which is probability of theta given x, so in this case, the posterior for the ith example would be probability of p. The theta parameter here is p, the probability of h given x of I, right? Which is then proportional to the prior term, which is probability of p, which is nothing but your beta distribution times the likelihood, which is the probability of xi given p, the expression for which we had derived in the last slide. So if you do this, if you compute this particular expression, you end up with an expression of this particular form, right? So interestingly, if you look at this particular expression here that we arrived, so now if you actually conduct n samples, right, n trials, then your complete posterior on the entire data, right, it takes this particular form. You assume the trials are independent, so the probabilities, the likelihoods multiply, and therefore you end up with an expression of this particular form. And if you actually end up looking at this expression, you will notice that this expression is nothing but the beta distribution characterized by these parameters. So now it kind of jumps out at you that by using a beta prior, your posterior also ends up being a beta distribution, right? So that is essentially the beauty of using a conjugate prior. And it, like I said earlier, it has a huge importance in terms of variational inferencing and so on. Right now, as I talked about earlier, there was a concept of maximum a posteriori probability, or MAP. The way we would do that is by maximizing the posterior in terms of the parameter theta, in this case p. If you did that, you would end up with an expression of this form: n plus a divided by capital N plus a plus b, where a and b, remember, are the parameters of the prior beta distribution, and n is the number of heads, and n is the total number of trials. Interestingly, now look at this case where, let's say, small n equal to 2 and big N equal to 2, right? So in this case, they don't really have an outsized influence on your probability estimates, because they are kind of regularized by the a and b parameters that appear in the expression. Whereas, let's say, if both small n and big N are, let's say, big N is large, let's say you conduct like 10,000 trials, then the parameters a and b that are appearing in the numerator and denominator pretty much lose their significance, right? I mean, the ratio is entirely determined by the value of small n and big N. So this kind of encodes, this estimate kind of encodes the confidence in the sense that when you have a large number of trials, it tends to pivot more towards what the probabilities that you observed basis the empirical estimates arising from the trials. Whereas if the number of trials is very small, then it gives sufficient importance to the prior distribution so that you don't go making absurd conclusions basis the data. Okay. So the idea behind training a Bayesian network is to be able to ask questions of this network and arrive at suitable answers that could either be point estimates or probability distributions. Essentially, there are three main types of inference. Marginal inference involves finding the probability distribution of a given node in a trained network. Posterior inference, we talked about the posterior distribution earlier. Posterior inference involves finding the probability distribution of a set of unobserved nodes given some other nodes which have been observed. And finally, the map estimates, map inference, wherein you want a point estimate of the unobserved features by maximizing the posterior probability. So we will look at these three inferences by taking the example of the student network. So as I was mentioning in the last slide, you have the three different forms of inference: the marginal, posterior, and map inference. So if you look at the marginal inference, one particular example in case of student network would be, let's say, finding the probability of L, where L is a letter and it can take on two values, 0 or 1. So the way we would estimate this marginal distribution is through a process called as marginalization, wherein you take the joint distribution and integrate out all the variables that you're not interested in. So for example, to find the probability of L, you would take the joint distribution and integrate out the difficulty, intelligence, grade, and SAT scores. Right. So this the summation itself can be made a lot more efficient by exploiting the graph structure and the particular form of the joint distribution, which allows us to move certain terms, in and out of the summations to make the process more computationally efficient. To give the example of posterior inference, so one particular example could be, for example, what is the probability of the letter given the SAT score is good, right? So in this case, again, you could use the joint distribution and arrive at an expression like this to be able to estimate this posterior distribution. And finally, an example of a maximum a posteriori inference, for example, could be where somebody asks you a question that you already trained this graph. Can you tell me what is the what values of the SAT score and the letter will maximize my joint distribution such that the difficulty is 1, intelligence is 0, and the grade is kind of good, right? So these kind of questions can be very effectively answered using the graph architecture and the joint distribution that we have just learned using the parameter estimation techniques that we described earlier. So in the last slide, we kind of looked at marginalization as a means to performing inference in Bayesian networks. But then that is not a process that is suitable for all practical purposes, right? Especially in the case of large graphs, marginalization becomes computationally inefficient, and in several cases it may not even be possible to use this particular approach to perform inferencing. So let's take an example. Let's say you have a graph with 6 nodes and you are interested in finding the posterior, that is probability of x1 given y1, y2, y3. So then the way you would do this is to marginalize out the features x2 and x3. So let's say the cardinality of the feature is represented by mod of x. So in this case, for let's say estimating the posterior for a given value of x1, you would have to perform mod of x2 into mod of x3 summations, right? And then doing this for all possible values of x1, you would end up with mod of x1 into mod of x2 into mod of x3 summations. So let's say in general, the cardinality of the feature space is S and the number of features is N. Then you end up performing close to S of the order of S to the power N computations or summations to be able to arrive at this posterior distribution. So this is kind of apparent that for large N, a large number of features and a higher cardinality, this computation becomes extremely inefficient. And for all practical purposes, for real world graphs, this is not an approach that is feasible. So to overcome this, we can use a technique called belief propagation, which is an iterative process in which neighboring variables, for example, x3 and x2, talk to each other, passing messages such as I, variable x3, think that you, variable x2, belong in these states with various likelihoods. So after enough iteration, this series of conversations, between the nodes is likely to arrive at a consensus that determines the marginal probabilities of all the variables. So in the case of graphs which don't have any cycles or loops, so these marginal probabilities or the beliefs are actually exact. That is, they converge exactly to the marginal probabilities of the nodes. So but not going into the mathematical details here, but the process kind of mirrors a dynamic programming slash Viterbi coding approach for graphs which have no loops, which makes the process a hell of a lot more computationally efficient than what you would have with marginalization. Okay, so then what is the problem? So we already discussed marginalization and said that that is extremely computationally inefficient, and therefore we kind of went towards belief propagation. But then it's been noticed that for large dense graphs, as for example, let's say a graph that would involve social networks or Twitters or something like that, in those cases also the belief propagation tends to become computationally inefficient. So that's where we come across the need for having a different approach towards performing inferencing on Bayesian networks, and two possible solutions emerge in terms of Monte Carlo methods such as Markov chain Monte Carlo sampling, and the second approach being variational inferencing. And both of these will be discussed in greater detail in part 2 of this presentation. All right, so with that, this brings me to the end of the part 1 of this lecture. I hope you are able to grasp the basics of probabilistic graphical models and have a good understanding of what graphical probabilistic models are, the way we perform parameter estimation on these models, and a couple of approaches for performing inferencing, and also what really constitutes inferencing in these models. So yeah, so thanks a lot for your attention. I would be happy to answer any questions at the end of this lecture, but do stay tuned for part 2 of this series. Thank you.
Hello, everyone, and welcome to this part of the tutorial. My name is Philip Schulz, and as you can see from the slide, I'm located in Melbourne, Australia. So the machine learning team in India of Amazon actually has a little outpost in Australia, and that's where I'm located. And what I'm going to talk you through today is approximate inference for probabilistic graphical models. So Graphical has already presented different flavors of graphical models and applications for them. And what I'm going to talk you through is inference for those. And in particular, inference for models where you can't find an exact solution, right? So Graphical has presented models where an exact solution may be possible, but more often than not, you won't find an exact solution. And in this case, you'll have to use what's called approximate inference. And we're going to go through what that is exactly. And we're going to go through two of the major techniques to accomplish approximate inference. So let us review the basic problem. The basic problem is really that we want to compute a posterior, right? So I have my observations X, and I have some latent variables Z, whatever they may be, right? For example, they may be pos tags, or they may be image segmentations. And I want to compute that posterior. So basically a distribution over these unobserved variables given my observations. And the problem is that we cannot compute px directly, because that would basically mean integrating over all latent values. And again, that's computationally just not feasible in most cases. So for the purpose of approximate inference, we're just going to accept that as a fact of life, right? We're not even going to try to compute p of x. We're just going to accept that we can't compute it. And then the question is, can we somehow compute this posterior directly without having to go through the normalization constant, which is p of x, right? And that is basically the problem we're going to tackle. And the goals for the session are as follows. So I'm going to present two general purpose algorithms that are straightforward to implement and can be used on most problems, not all of them, but most problems that you'll encounter with probabilistic graphical models. And I should say that for any specific problem, you'll find specialized algorithms that will work better. So for example, in the case of thin Markov models, for example, you'll have a specialized algorithm that computes those exactly, or that computes the posterior exactly, rather. And again, like even for nonlinear, non-conjugate models, people have come up with all kinds of intricate specialized algorithms. That's not our goal here. What I really want to present is two general purpose algorithms that you can just apply out of the box and that will just work for most problems. But bear in mind that there may be a better solution around for any particular problem that you have. At which point you might ask, well, why would I use these general purpose algorithms in the first place then? Well, oftentimes when you start working on a modeling problem, you do not exactly know which one the best model is, and you may want to try out different model variants. And that's where general purpose inference algorithms are great, because they don't limit you to a particular class of models, right? You can just change out your likelihood, you can change out your priors, you can make all kinds of additional assumptions, and these general purpose inference algorithms that I'm presenting today will still accommodate those. That being said, we will provide references to extensions, right? So these algorithms that I'm presenting are basically the bare bones algorithms, and obviously there's a whole lot of research on how to extend them and make them better. And I'll just point you into the general directions, right, where you can then follow up and read up on. So the algorithms that we're going to look at in particular, not algorithms, rather classes of algorithms, are variational inference, which basically casts posterior inference, so computing this posterior distribution, as an optimization problem. And it has the advantage of being relatively quick. It's easily parallelizable because, as we'll see, it's gradient-based. So basically, it's a gradient-based optimization method. And there we can just borrow from all the work that has been done in the neural network space, right? We can easily parallelize gradient computations across multiple GPUs or potentially even multiple machines. It puts some burden, variational inference puts some burden on the user in that the user has to choose the posterior. So what variational inference actually does is it optimizes a family of distributions to approximate the posterior. And what that family of distributions is going to be, so when I say family of distributions, what I mean is something like a normal distribution, a logistic distribution, student t distribution, all of these things. So the user has to choose one of these parametric families to then be able to approximate the posterior. And variational inference can be a bit tricky for discrete variables. And in particular, it may lead to bad approximations. So it's what I said before, right? You choose a family of approximations. Now, say you have two modes, right? So you have a posterior distribution that has two humps, and you choose to approximate this distribution with a Gaussian. Obviously, there's no way you can perfectly fit this posterior because the Gaussian only has one hump, right? So according to what distribution you choose as an approximation, this approximation may be very, very bad if it doesn't like comply with the geometry of the actual posterior. And on the other hand, we're going to look at Markov chain Monte Carlo or MCMC methods. These methods are potentially very slow, but they're kind of seen as the holy grail of approximate inference because they're asymptotically correct. What do I mean by that? Well, asymptotically correct just means that if I run these methods for long enough, then I will actually recover the true posterior, or at least I will recover samples from the true posterior. Now, when I say long enough, the problem here is that nobody really knows what long enough is, right? So what we usually do as a heuristic, we just run these methods for as long as we can, and we cross our fingers that they have actually converged to the true posterior and that are generating samples from the true posterior. But because of that, they can be painfully slow. However, if you have the opportunity to at least get one MCMC run in, even if, say, in production or for other purposes, you want to use variational inference, it's still always a good idea to run MCMC for the simple reason that it will provide you a ground truth, right? So it'll actually inform you about the shape of the posterior, and it'll also inform you about the quality of other approximations. So say if you're using variational inference, if you run MCMC first, you may get a rough idea of what the posterior looks like, if it has one hump or two humps or multiple humps. And according to that, you may then want to choose your variational approximation. All right, so let's dive into variational inference first. So as I already said, the idea is to choose a parametric family for the approximate posterior. Generally, people choose Gaussians. You could choose anything else really, but for the moment, for the time being, let's assume it's a Gaussian, yeah? And then you're gonna optimize the parameters to match the posterior closely. So here, the blue distribution or the blue histogram is the posterior. So it's the distribution over our latent values, given that we have observed the data. And Q, so Q is just like the general way of expressing the posterior distribution, the approximate posterior in variational inference. Q of Z is the approximation. And as you can see, they're fairly wide apart. So at this point, it would be a bad approximation, right? Because Q and P don't really overlap. And what we do in variational inference then is via gradient ascent or descent, whatever you want to call it, we're trying to move this yellow curve Q closer to the blue curve P, right? And in the ideal case scenario, they'd be fully overlapping, which would mean that we'd have recovered the true posterior. And again, most of the time in reality, that's not going to happen, but we can still try to push Q as close as possible to P. So what are we actually trying to optimize here? What is our loss function or objective? Well, it's traditionally the KL divergence of the posterior from the approximation. And many other divergences have been proposed, but we're going to go with the classical one here because that's still the one that's overwhelmingly being used. So the KL divergence of the posterior from the approximation. And what we're going to try to find actually is the parameters of the approximation that minimize that KL divergence, right? So that's going to be our optimization problem. And oftentimes we don't only want to do that for inference. So not only do we want to approximate the posterior, but we will also want to train the model at the same time. And for the rest of this talk, just remember that lambda is going to be our variational parameter, so the parameters of the approximation, and theta is going to be our model parameters. So in particular, then what we can do is we can optimize this KL divergence for the model parameters and the variational parameters simultaneously. And then it becomes kind of a, it could be interpreted as an alternating optimization. Think about expectation maximization, for example. But actually what we're going to do is we're going to use gradient descent and just optimize all of these parameters together. So again, the important difference here being that we optimize lambda to build a good variational approximation to the posterior. So that's the inference part. And we can also, if we so choose, simultaneously optimize over theta and thereby also optimize the model parameters and just get a better fit to the data. Okay, now let's get into the weeds and look at the negative KL divergence a bit more in detail. And I'm talking about the negative KL divergence here just because it's going to be easier to handle mathematically. So in particular, if we look at this negative KL divergence and we just write it out, what we get is the second line here, right? So that's literally just the textbook definition of what a negative KL divergence is. And now we're going to apply some algebraic manipulations to make all of this a bit more digestible and to get it into a form where we can actually work with it for the purpose of automated inference that we can run on our computers. Okay, so first of all, I'm going to separate out this ration here. So in particular, we have the numerator on the left side and the denominator on the right side, right? Oh yeah, and one other important thing to note is that the expectation here is taken with respect to the approximation. And again, that's just by the definition of what a negative KL divergence is. Okay, so we separate out the numerator and the denominator. And for the enumerator in particular, so for the posterior that we've been working with, we further separate out 1 over px. So again, remember that px is exactly the quantity that we can't compute to start with, right? So the reason that we are using approximate inference is we can't compute px. So for as long as px is in here, this is actually completely useless because we are back to square one, right? We still have px, still can't compute it. So this expression here doesn't make our lives any easier. But what I can now actually do is, since px does not depend on the measure of expectation, I can pull it out entirely, right? And also notice that here we have a negative expectation over the approximate posterior. And this negative expectation is really just the entropy of the posterior, right? Okay, now what have we accomplished really? Well, remember that we want to minimize with respect to the variational parameters lambda. So where do we have a lambda? Well, we clearly have it here in this expectation, and we also have it as part of the entropy. Log P of x does not contain any lambdas, right? Which means that when we are optimizing for lambda, this is just a constant that we can neglect. And this is awesome, right? Because that's what we wanted all along. We want to get rid of P of x, and that's exactly what we have accomplished. So what we can do then is just maximize over this expression, because it's a negative KL divergence, right? So we want to minimize the KL divergence, which is equivalent to maximizing its negative. And we're just going to maximize over this last line. And importantly, we're going to drop log P of x, right? Because it's a constant with respect to our optimization problem. And suddenly, this whole thing becomes computable, and we can actually solve for it using gradient descent. So that's the whole magic behind variational inference at the end of the day. And this thing in the lower box is called the evidence lower bound, or ELBO. That is going to be the objective we're optimizing for in variational inference. Okay, so how do we solve this optimization in practice? Well, on one hand, as I already pointed out, we could use coordinate ascent, where first we're optimizing for lambda, then we're optimizing for theta, optimizing for lambda again, optimizing for theta again. So kind of an alternate optimization procedure. That's very akin to what often happens in expectation maximization. But no, that's not what we're going to do today. Today, we're just going to solve this problem like we basically solve all optimization problems these days via gradient descent, right? Okay, so let us apply gradient descent. And I'm going to start out here with the model parameters. And in like about 3 minutes, you'll see why, right? So I'll first take the derivative with respect to theta, our model parameters. So notice that the entropy here does not contain any thetas. So again, it's a constant. We can throw it out for the purpose of optimizing theta, right? And then we just have that the expectation operator is linear. So what we get is the gradient of the expectation is actually the same as an expectation over gradients. And that's great, because while the exact expectation may be very hard to compute or even impossible to compute, we can actually approximate it via sampling. And I'm using LL here to denote the law of large numbers, which basically just says if you're drawing enough samples, you'll recover this expression exactly, right? And what are we drawing samples of? Well, we're drawing samples of our latent variables because this expectation is over latent variables, right? So this expectation is over Z. So because it's an expectation over Z, and in particular, it's our approximate posterior, right? We're going to draw samples from this distribution here, from the approximate posterior, plug them into the log joint, and take gradients with respect to that. And I'm not going to go further into the exact details of how to compute these gradients here for two reasons. First of all, I don't even know what model we are assuming, right? It might be a simple linear model like Bayesian linear regression, or it might be some crazy Bayesian neural network. But also, I don't really have to care about this because, as I said before, we can really piggyback on the advances in neural networks and use automatic differentiation libraries. So this gradient here will be computed for us by some library. So we don't really need to care about how to compute it exactly. The only thing we do need to care about is that we draw samples from the approximate posterior, plug them into the log joint, and then average over the gradients that are computed automatically. Now there's one practical tip. I said the law of large numbers basically tells us if we draw infinitely many samples, we're going to recover this expectation exactly. Turns out that in practice, often one draw of that can be enough. So although it may seem that theoretically you'd have to draw a whole lot of values of Z to get a meaningful approximation here, oftentimes it suffices to only draw one value of Z. And in general, any small number smaller than 10 or 10 will suffice to solve even very, very complex optimization problems in that domain. Okay, so now let's look what happens if we differentiate with respect to lambda, our variational parameters, right? So before we've been optimizing the model, now we're optimizing the variational approximation. And what you can see immediately is that when we're taking this derivative with respect to lambda, we can't just push it inside the expectation as we did with the derivative with respect to theta. And why is that? Well, the expectation itself is taken with respect to a distribution which has parameters lambda. So yeah, that won't work. So what we would have to do is compute the entire expectation first and then take the derivative with respect to that. But the problem is that in general, we won't be able to compute this expectation exactly. And why is that? Well, we have these terribly complex models, Bayesian matrix factorization models or Bayesian neural networks that are just really hard to compute expectations of. So we'll have to do something else. And what we're going to do is actually a pretty old result in mathematics, which is variable switching. So in particular, we'll try to find a variable epsilon and define a mapping between epsilon and Z. So both epsilon and Z are random variables. However, the trick is to design epsilon so that it does not depend on lambda, right? Because we want to get rid of this lambda here in the expectation in order to then push the gradient operator inside the expectation. Okay, so basically what we need to find is a mapping that maps Z to epsilon. And we have a couple of requirements for that mapping. So the first one is that it be a bijection or that it be invertible, right? So for each value of epsilon, I shall be able to map it to a unique value of Z. And likewise, for each unique value of Z, I shall be able to map it to a unique value of epsilon, right? So we basically have a function g that maps epsilon to Z. And we have a function g inverse that maps Z to epsilon, right? So we can basically what I'm saying is we can go back and forth between Z space and epsilon space. And another requirement that we have for this function is that it be differentiable, because in this entire process, we are going to be dealing with derivatives because we're using automatic differentiation. We actually need it for variable switching itself. But yeah, let's just go with the argument of computing gradients here. So in order to compute gradients, we will need G to be differentiable. Okay, And then what about epsilon itself? Can that be any variable? The answer is yes. In principle, it could be any variable. But I'm going to foreshadow what we're going to do next, right? So we're going to again have an expectation, and we're going to again want to approximate that expectation via sampling. So we will have to draw samples from epsilon. So while theoretically epsilon could be any variable at all, for convenience sake, it should be a variable that we can easily sample from. And automatic differentiation variational inference, which is the algorithm, the concrete algorithm that I'm going to present today, fixes that problem by always drawing from a normal distribution. Okay, so we're always going to have epsilon be a normal distribution. And then the task basically becomes to find a mapping from our variable z to a normally distributed variable. Once we have defined such a mapping, we can then do the following. Instead of taking the expectation with respect to z, we take it with respect to epsilon. And here I use phi as a notation for the standard normal distribution. So the standard normal distribution is a normal distribution with mean 0 and variance 1, right? And standardly that's defined as, that's denoted by phi, right? So phi of epsilon is just a standard normal distribution of epsilon. So we're going to replace the expectation over z with an expectation over epsilon. And then this term in here needs to be defined entirely in terms of epsilon, right? Because we have switched the variable z to the variable epsilon. So we cannot make any direct reference to z anymore. So we somehow need to compute z in terms of epsilon. And that is exactly what our mapping G is for, right? So G is going to compute the value of z for us, given a particular sample of epsilon. And you can see how the sampling process works here, right? So before we would draw samples from z directly, now we draw samples from epsilon, map them through G, and that will give us a sample from z. And then another thing to pay attention to is that we'll need to add the derivative of that function, G, which is referred to as the determinant. And it's a determinant because generally we're going to have multivariate functions. So z and epsilon might be multidimensional, say 2-dimensional, 10-dimensional, 100-dimensional, right? And then in that case, instead of just having a single derivative here, we'll have a matrix of gradients. And that matrix is called the determinant. And again, that is something that we can usually compute rather straightforwardly. And why? Well, because we know G, right? We have chosen G ourselves. So we can choose G in such a way that we can easily compute its gradients. And there's an entire theory around how to compute these determinants, or rather how to choose G such that the determinant is easily computable, which I won't go into here today, right? Just let it be known that once you have defined your function G, it needs to be such that you can easily compute the derivative so that you can have this determinant factor here. Why do you need the determinant? Well, it's basically a volume correction. So in particular, if you think of both z and epsilon as Gaussian variables centered at 0, and the only difference being, say, that z has a higher variance than epsilon. So we know epsilon has unit variance, so variance 1, and say z has variance 5, right? And then basically the support, the region on the line that z has meaningful probability mass on is going to be larger than that of epsilon, right? What that is basically a volume expansion on the real line. And that volume expansion, or in this case, volume contraction, because we're going from z to epsilon, so we're actually shrinking our variance, needs to be accounted for. And that's exactly what the determinant is doing. So think of the determinant as a correction factor. Then you need to introduce, and why do you need to introduce it? Well, because you have switched from variable z to variable epsilon. Okay, so that's the theory, but really the amazing and very useful consequence is that now we don't have any lambdas here. We can push lambda inside. And also the entropy is usually a quantity that we can compute exactly. So you can go to Wikipedia, right? So if we assume that Q is a normal distribution itself, then you can just look up what the formula for the normal distribution is on Wikipedia. Plug that in here, and again, the gradients will be computed automatically for you via automatic differentiation. Cool. And then what we're going to do is we're going to basically use the same strategy as we did before, where instead of computing this expectation over gradients directly, we're going to sample from epsilon. For each sample, we're going to compute this quantity here, the gradient here, and we're going to average over that. Okay, so let's go into applications. And applications are important for two reasons. Well, first of all, they motivate what they're doing. But in this particular application, I will also be able to very succinctly show you the consequences of what I've just derived theoretically. So what I want to talk about as an application are variational autoencoders. Variational autoencoders are basically an extension of the classical autoencoder. So what does an autoencoder do? Well, it takes a data point X or data vector X and maps it to Z, right? And Z is going to be some latent representation. And what the autoencoder can do is basically it can encode X as Z and it can decode from Z into X. So basically, given this latent representation Z, it can decode the data point that we had before. So for example, X might be an image. And then you can think of an autoencoder as an image compression machine, right? Where generally the image, say, has 728 pixels. The encoding Z will only have 200 entries. So basically, I'm shrinking the encoding of X. And then likewise, I can use the representation to recover X, so to basically regenerate that image. Now, there's one problem with classical autoencoders, which is if I'm choosing a latent representation Z that has no correspondence in like the images that I've encoded initially, and I ask the autoencoder to decode that latent encoding Z into a new image, oftentimes it fails, right? Because it's just Z is drawn from a point in latent space that the autoencoder has not been trained on, and therefore decoding will fail, and the image that I'll get in return will just be gibberish. The variational autoencoder addresses this problem to some extent by encoding X into a distribution over latent values. So instead of mapping X to a unique latent value, we'll now map X to a distribution over latent values. And that basically has a regularizing effect. And as I mentioned before, there are now fewer gaps in latent space. So what I can actually do, and which is really cool, I can basically make up encodings, right? I can use random encodings and ask the autoencoder to decode these for me and thereby generate new images. And it's not only images, right? So VAEs have been applied to text generation for things like politeness, right? So the latent space would then be used to encode politeness in latent space, and for example, to transform an impolite sentence into a polite sentence. There's even one really cool paper which takes modern day English and transforms it into Shakespearean English using variational autoencoders. There's sound generation where you may want to manipulate a song or something that somebody has said. VAEs have also been used in causal inference, where basically the task is to find the effect of an intervention. So for example, in drug trials, what is the effect of administering this drug versus not administering this drug? And then again, controlled language generation would be things like politeness, potentially also machine translation, where you're trying to translate from one language into the other, right? I'm going to stick with the image example though, because I think it's the most, at least in the presentation, it's the most impressive. So this is a rather recent paper where VAEs have been used for image generation. And the cool thing about these photos is that they're not actually photos. So these people that you see here don't exist, right? But rather they were generated exactly in the fashion that I had mentioned before, where random image embeddings were generated and the autoencoder decoded from these random image embeddings and came out with these faces over here, which again, they're not real people, but they're just generated from a latent representation. So that shows you the kind of, first of all, the powers that variational autoencoders have, but also the potential utility, right? So for example, you may use them to augment your data when you're training a facial recognition system, right? You only have pictures of so many people in your database from so many angles, but obviously more people are out there, and B, more people are going to be born each day who bring their own faces to the world, right? And you cannot possibly train on all people. But what you can do is you can generate random faces, so to speak, and use those to augment your training data for your facial recognition machine. Okay, and now let's look at the computation graph, right? So now we're going to put the mathematics and the actual implementation together. So we're going to start out with an observation X, which again might be an image in this case. And we want to get back to X, right? So we want to reconstruct X. And that is basically going to be the encoding up to Z and the decoding part from Z to X. And I've colored X in here because it's going to give us the joint density over Z and X, which was part of our objective. So we actually need that in order to compute the elbow and derive gradients with respect to the elbow. In general, I'm going to color all nodes that are related to the objective in blue. Okay, so what's happening here? So we're going to use X and use the variational parameters lambda that we assume have already learned, or at least learned to up to a certain level. And we're going to infer what? A mean mu, a Gaussian mean mu, and a Gaussian standard deviation sigma. And why would that be a Gaussian mean and a Gaussian standard deviation? Well, remember what I said, right? Generally, we're using Gaussian approximations. And we could potentially use other approximations. I'm going to use a Gaussian approximation in this case, just because it's the easiest thing to do, and it's actually what most people do in most applications, right? So more often than not, our variational approximation will be Gaussian, and that's exactly the example that we are going with here. So we are computing the variational mean mu and the variational standard deviation sigma using our variational parameters lambda. And I'm being deliberately vague here about what these variational parameters lambda are, but they might be maybe anything at all. And in particular, in the variational autoencoder, they're going to be neural networks, right? So this might be a feed-forward layer, that might be a full-blown ResNet because we're dealing with images, right? So a ResNet would make sense here. Any architecture that you can think of, really. And the parameters of that architecture, I'm going to collectively call them lambda. Okay, so now once we have the variational mean and variance, we somehow need to compute Z from them. Or rather, we need to sample Z from them. And this is where our trick with the introduction of the variable epsilon comes in. So we're now going to introduce epsilon. Sorry, I should have said that this thing here is generally called the inference model, and this thing here is called the generation model. So as I said before, the inference model encodes the observation X into latent variable Z, and then the generation model decodes it from the latent variable Z into an observation. But what we are concerned with now is mapping this variational mean and standard deviation to a sample of Z. And this is where the mapping from epsilon comes in. So I told you need to find a transformation from a standard normal distribution to your target, to your variable of choice, to your variational approximation. And it turns out that for Gaussians, that is particularly simple, because to transform a standard normal distribution to any other normal distribution is simply done by taking the mean and adding the standard deviation times a sample from a standard normal distribution. Okay, and that's how we'll get Z here. Notice, however, that because epsilon, the sample, is kind of hanging around on the edge of the computation graph, we can compute all gradients fine. So in particular, we're going to have gradients flowing back from our loss function all the way to Z, and then through mu and through sigma, all the way back into our variational parameters lambda. If we sampled Z directly, right, gradients of samples, nobody can take gradients of samples, right? So basically the gradient flow would stop here, and we would never be able to update our parameters lambda. And that's exactly what we've seen in the theory section. If you remember, we were able to compute the derivative with respect to theta just fine. It was the derivative with respect to lambda that was giving us trouble. And it's the same here. If we were to draw samples of Z directly, yes, we could still compute the parameters with respect to theta. We would not be able to compute the parameters with respect to lambda. However, because we did the variable transformation trick and because the sample is now at the edge of the computation graph, gradients can flow through this computation graph nicely, and we get all the gradients that we need to update both our model parameters theta and our variational parameters lambda. Have I forgotten anything? Well, yes, I have. We still need to have the entropy term, which again contributes to our loss term. That's why I've colored it in blue. And it only depends on the standard deviation. So that's just a fact of Gaussians, right? So the entropy of a Gaussian only depends on the standard deviation, not on the mean. For other variables that may be different, right? So there may be a variable where we also need to condition on the mean in order to compute the entropy. And finally, I told you that we need a determinant in order to correct for the volume expansion. As it turns out, and I'm not going to go into any details here, if we are mapping from a Gaussian to another Gaussian, so in this particular case, if we are mapping from, a standard normal distribution to any other normal distribution, the entropy term actually, the determinant term actually cancels. So in this particular case, and this is another reason why this Gaussian approximation is so well loved among practitioners. In this particular case, we don't actually need the volume correction term. We don't need the determinant. Once the transformations become more complex, we will need the determinant term. And I just encourage you to look at the ADVI, or automatic differentiation variational inference paper, to read up more on that, right? But whenever you're using a Gaussian approximation, that is all you need. So you'll have your loss with respect to the joint over x and z, and you'll have your loss with respect to the entropy, and that's going to be it. Okay, now I also want to show you some code that is actually available on GitHub for how you would actually implement that. Notice that this is implemented in MXNet, so don't get too hung up on the details. I really just want to get you like the rough idea of how you would code this in Python. So what we're going to have is we're going to have an inference net, which, given some data, computes the mean and standard deviation of the Gaussian. We're also going to have some sampling method that takes the mean and standard deviation as input and gives us a latent state. So that is basically where we are generating from a standard normal distribution, applying our transformation, and then we get our latent state, which would correspond to Z in the graph, right? So the latent state is the same as Z. And then we're going to have what I call KL loss here, because it has a slightly different formulation of the L, but think of it as the entropy, right? So that's the entropy loss. And we're going to have the log likelihood loss, which is basically a loss on the reconstruction X, right? That basically tells us how well or badly we have managed to reconstruct the observation, the input image X. And in the end, we're just going to group these losses, and what MXSim group does is it just adds them up, right? So there's literally going to be the joint density of X and Z plus the entropy term. Let us look into some of these a little more closely. So in particular, in the train method, we're just gonna, so this is actually for pixel generation, where the pixels are binary. So this is just basically computing the loss with respect to X and Z. So the likelihood with respect to X and Z. In this case, it's a Bernoulli likelihood. It might be anything else, right? What's more interesting is the sampling of the latent state. So up here, we have some bookkeeping related to reshapes and dimensionality, which is really not something you should worry about at the moment. The main thing is that how we map the standard normal variable epsilon to our variational approximation Z is, as I've said before, we take the mean and add the standard deviation times a standard normal sample. So in particular, this part here, the draw from a normal distribution with location 0 and scale 1, that's epsilon, right? So really it's just mean times standard deviation, mean plus standard deviation times epsilon. Okay, so yeah, that's basically the core of the implementation. And as you see, it's one line. So although we went through quite some heavy math and we did quite some heavy lifting on the theory side, surprisingly and nicely enough, what we end up with is a one-liner. And that's also why I said in the beginning, it's a general purpose algorithm that's pretty straightforward to implement. Some concluding remarks on variational inference, and there's some practical considerations. In particular, oftentimes we make a mean field assumption, which really just means that the posterior or approximate posterior factorizes over its dimensions. If we think of Gaussians, all this means is that your covariance is going to be diagonal. So instead of having a full covariance, we're going to use a diagonal covariance. It's just a simplifying assumption, which in particular in the case of Gaussians is mostly for memory considerations, because if you're dealing with really big models and you have lots and lots of latent variables, each of which has like a high dimensionality, then storing full covariances for these, which would basically have the dimensionality of the variable squared, is just not feasible in terms of memory. So that's why we usually assume that the approximating Gaussian just has a diagonal covariance. That limits our approximation, obviously, because if there's covariance structure in the true posterior, again, we're not going to be able to capture that. And another practical consideration is that the KL divergence tends to, or the optimization of the KL divergence tends to underestimate posterior variance. So if you get really small variance with your variational approximation, chances are that the variance of the true posterior is actually larger than that. So if you're in doubt whether you should trust your variational approximation on the posterior variance, probably not. The true posterior variance is probably going to be a little larger than what the variational approximation gives you. Further topics to read up on are the Gumbel softmax. So that's being used for discrete variables, right? So far we've only been talking about continuous latent variables, so in particular Gaussians. If you want to use discrete variables, you may want to look at the Gumbel softmax. And there's a whole other way of doing variational inference, where instead of this mapping from one variable to another, you're doing something entirely different. And that's called the score function estimator, also known as reinforce. And the best paper, in my opinion, to present that idea is Paisley et al. 2011. So that's definitely something worth looking into. The advantage of the score function estimator, it's harder to implement. It comes with all kinds of separate problems. The advantage is that it handles both discrete and continuous distributions effortlessly. So instead of having to think up something like the Gumbel softmax trick, which handles discrete variables in the case of reparameterization, so in case of the method that we have just seen, the score function estimator just handles all of them effortlessly. Comes at the price at being a little bit harder to implement and needing more fine-tuning. And another topic that you may want to look into that's very dear to my heart is normalizing flows. So we've talked about how oftentimes the posterior will have weird shapes. Like, for example, it may have 2 or 3 or 5 or however many humps, and you're approximating that with a Gaussian. Because the Gaussian only has one hump, your approximation is going to be bad. We've also said that generally you don't know what the shape of your posterior is going to look like. So basically, when you're choosing your posterior approximation, you're kind of fishing in the dark a little, right? Yes, you're going to use a Gaussian because it's a simple thing to do, but really you have no clue what your posterior looks like. Normalizing flow are learned posterior approximations. So instead of saying my posterior approximation is definitely going to have a Gaussian shape, normalizing flows allow you to say, I have no clue what my posterior looks like. So let's learn the posterior shape along learning the variational parameters. And normalizing flows allow you to do that. They're a very powerful tool, but unfortunately, they're a bit outside of the scope of today's lecture. All right, that was everything I want to say about variational inference. Now let us move on to Markov chain Monte Carlo methods. Just as a reminder, Markov chain Monte Carlo, in comparison to variational inference, it is more precise. It will give you samples from the true posterior if you draw enough samples, but nobody really knows what enough means, and you may just spend a long time sampling from the posterior. Yeah, so that's the trade-off here. So Markov chain Monte Carlo is going to be a more precise, more accurate method that unfortunately, though, you won't really be able to apply in many practical scenarios, just because it takes a long time. And especially if you're dealing with big data, it's just not going to be feasible to run it for long enough. However, if you're dealing with medium-sized data, where when I say medium-sized, we are talking maybe 100,000 images, Markov chain Monte Carlo might actually work really, really well. So what's the idea behind Markov chain Monte Carlo? Well, before we skip to Markov chains, I'm just going to tell you the Monte Carlo part. So Monte Carlo is actually the capital of Monaco, which is a dukedom at the south coast of France. And that dukedom is known for one thing, or two things actually. It's a tax haven, so lots of rich people go there to evade taxes. But also it has a casino, and the casino of Monte Carlo is well known, has featured in several James Bond films, amongst others. And that's basically where the name of Monte Carlo techniques derives from, because Monte Carlo techniques depend on randomness of the outcome, just as gambling has a lot of randomness in it, obviously. Okay, and to give you a feeling for what for what Monte Carlo methods are doing, let's look at the following image. So we have a circle, right? And what we want to do is we want to approximate the area of that circle, where the area is pi, right? Okay, so computing pi exactly is basically impossible. I don't think there's a closed formula for pi. So all we ever can do is really approximate what the size of pi is. And the way we're going to approximate that is as follows. So we have the circle here, right? That's the blue line. And do you see these dashed lines around the circle? So we're just going to focus on the lines ending in 1 and -1, right? And then you can see that what we actually have is a square around the circle, where the square and the circle are touching at 0. Yeah. And drawing samples from a square, uniform samples from a square, is relatively straightforward because, well, I know the area of a square, I know how to compute it. And once I know how to compute the area, I can just easily draw samples from that area uniformly, right? So, and that's exactly what I'm going to do. So I'm going to draw uniform samples within that square. Okay. And in this first instance, I've drawn 10 samples from the square. And as you can see, 3 samples are outside the circle and 8 samples are inside the circle. Now, what I need to do in order to find pi, which is the area of the circle, is I basically know what the area of the square is. It's 4, so 2 by 2. And I just need to check how many of the points are inside the circle and how many are outside the circle. And this fraction, the number of points inside the circle over the number of points times 4, is going to give me an approximation to pi, because 4 is the area of the square. And I'm going to have a fraction smaller than 1 of points that are inside the circle. So in this case, as I said before, I think there's 3 points outside the circle. So inside the circle are 7 points. So 7 over 10, or 0.7 times 4, is going to be my approximation to pi. So in this case, it's 2.8. If you know the value of pi, not a great approximation, not really. So what can we do then? Well, as I said before, in Monte Carlo techniques, the more samples you draw, the more accurate you're going to be. So instead of drawing 10 samples, let us draw 1,000. As you can see, they're like very evenly distributed across the square, which is good. That means we are sampling correctly uniformly from the square. And again, we're looking at how many points are inside the circle, how many points are outside. I can't really tell you how many. I just know I've defined this function here that basically computes this fraction for me, right? And basically looks at how many points are inside the circle. And if we multiply this by 4, the area of the square, what we get is 3.104. Much, much better approximation to pi. Still not exactly great. So let's draw 100,000 samples instead. And I'm going to warn you, I don't have a picture for the 100,000 samples because all you'd see is orange, right? So the circle would be completely overwhelmed by the dots that we're drawing from the square. But basically, if we draw 100,000 samples, our approximation to pi is this here. And then if we look at the exact number of pi, we're pretty close. We're actually hitting it up to the third digit after the comma, right? And that is the magic of Monte Carlo. The more samples that you draw, the closer you are going to come to the exact value. And in particular, if instead of drawing 100,000 samples, we drew 100 million samples, chances are we'd be hitting pi very, very exactly. Okay, and that is exactly what we're going to do with our posterior. So instead of approximating the posterior with another distribution, no, we're going to draw samples directly from the posterior. And now you may say, but wait, how do we sample from the posterior if we can't even compute it? So let us turn back to the original problem of Bayesian inference, namely that we can't compute the posterior exactly because we can't compute P of X, right? The marginal over X, our data. And I'm going to call X the reference density here, because what it does essentially is it normalizes the joint density over Z and X, right? So now, what if we could swap out this reference density, which we can't compute, for another density, which you can actually compute? That's kind of the underlying idea here. And the way we're going to do that is by approximating, again, that reference density P of X that we can't compute. How are you going to approximate it? Well, let's look at P of X. What is it actually? Well, it's a marginal over Z when we take the joint of X and Z. And what we're going to do now is we're going to introduce another reference density Q of Z, which we can compute by design, right? We're going to choose a density which A, we can compute, and B, that we can sample from. However, we can't just introduce that new density as a reference density. What we actually have to do is we multiply the joint density Pxz by 1, where 1 here comes in the disguise of Qz over Qz. And what that gives us is an expectation over this ratio Pxz over Qz. And just as we did with variational inference, we're going to approximate this expectation using Monte Carlo, so sampling. And there's one crucial difference to what we did in BI. So in BI, I said often one sample, maybe 10 samples is enough. Well, here we'll actually have to draw a lot of samples. So we're kind of in that scenario with the circle and the square, right? Where in order to approximate the area of the circle correctly, we need to draw lots of samples from the square. And it's the same thing here. So in order to approximate Px closely, we'll need to draw a lot of samples, possibly thousands of samples from Qz. But the good thing is two things. So first of all, this is going to give us an unbiased estimate, meaning we're going to recover Px exactly if we're drawing enough samples. Where again, in practice, we'll just have to limit ourselves to a finite number of samples. But also we don't need Px anymore, right? So we're actually approximating Px through sampling from another reference density. So that's good news because it again removes this limitation that we have of not being able to sample from Px. There are a couple of limitations here. So first of all, we're only computing a density, a marginal over X. But really what we care about most of the time is like some statistic of the posterior, right? Where the posterior is Z and X is just the data that we have observed. Now, there is a technique called importance sampling, where we're actually using this ratio Pxz over Qz for each sample as a weight. And then as we compute the statistics, we'll just compute the statistics over our samples of Z. But each sample is weighted according to this ratio. So that will then, actual importance sampling is a bit more complex than that, but the main idea is that the samples are weighted by this ratio here. And that will then give us or allow us to compute sample-based empirical statistics over the posterior. However, there are several problems with that technique, and that's why we'll actually add on Markov chains to the Monte Carlo methods. But let's first review the problems that we have when we're just using these weights, right? Either to compute the density, the marginal of Px, or in order to weight samples. Well, the density is basically the following. Again, just as a variational inference, Q of Z might be badly chosen. And if that is the case, the weights will be very far apart. And in particular, one sample might dominate all the others simply because it has a high weight and all the others don't. So if we are here assume that the density, our target density, the posterior, would be the small circle, the orange circle, and our proposal density or reference density is the blue circle, then the following is going to happen. Most samples are not going to be anywhere close to the actual posterior, right? Meaning they'll receive very, very small weights. And then the 1 or 2 samples that hit the posterior will receive high weights. And that does two things. First of all, are these samples that receive high weights representative for the statistic of interest? We don't know. But second, it will introduce a lot of variance, right? Because there will be variance in the weights. Lots and lots of weights will be very small. There are some weights that will be very high, which means overall, if we take the variance of all samples, or rather over the weights of all samples, we'll get a very, very high variance, which then again means that our estimator, that sample-based estimator, becomes very unreliable. And I'm showing you this here in just 2 dimensions, right? And there you can kind of see, yeah, if we choose QZ badly, then we have very little chance of actually hitting the posterior. It's even worse in high dimensions. So now if you imagine this problem in like 100 dimensions, 1,000 dimensions, it gets exponentially worse, right? Because the volume that we're dealing with is much, much larger than what we see here on the 2D picture. So basically, for most practical applications, and if the shape of the posterior is somewhat complex, we can't really apply this technique. We have to do something else. And that something else is, instead of drawing independent samples, we'll try to draw correlated samples. And we'll do that through Markov chains. So Markov chain Monte Carlo will give us correlated samples, which has the drawback that the samples are not independent anymore, and therefore we can't really count them as like 2 independent samples, right? Turns out it's not too much of a problem. All it means is that we have to draw even more samples, because until we get from a sample to another sample where they're truly uncorrelated, we'll have to pass through a wide, depending on how well your sampler works, but potentially we'll have to pass through a long line of correlated samples until we get 2 samples that are actually uncorrelated. So Markov chain Monte Carlo allows us to alleviate some of the problems that we are facing with just that naive sampling strategy that I showed before, but we'll have to draw even more samples. The nice thing is that we still have the convergence guarantees. So if the Markov chain is constructed appropriately, then again, we'll still recover the posterior exactly, or samples from the posterior at least. And what does it mean to do Markov chain Monte Carlo instead of Monte Carlo? Well, it's simply a change in the reference density, where the Markov assumption just means that each sample depends only on the previous samples, but not the samples before, right? So if I'm drawing 1,000 samples and I'm drawing the 1,000th sample, that sample will only depend on the 999th sample and not the other 998 samples, right? So yeah, our reference density will now always condition on the previous sample that we drew before. And there's a classic algorithm called the Metropolis-Hastings algorithm that accomplishes exactly that. So that allows us to define a Markov chain and then move from sample to sample. And its ingredients are basically as follows. So at each point, we draw a new sample from the conditional distribution that conditions on a previous sample, and then compute an acceptance threshold, where I don't really want to go into the details of the acceptance threshold at the moment. Just notice that it basically gives a threshold for whether or not to accept the sample, right? And then we basically draw from a uniform distribution between 0 and 1. If our draw is below the acceptance threshold, then we'll accept Zj as a new state. Otherwise, we'll reject that current proposal Zj and use the previous sample instead. So notice that that means that although we're transitioning from sample to sample, autocorrelation between the samples, so I said before, right, the samples are not independent anymore, but they're correlated. Autocorrelation between these samples may be perfect. Namely, in the case that we reject the new proposed sample and just keep the old one, because then 2 consecutive samples will be identical, right? And until we accept a new sample, we'll just stick with this one sample, which again also means that if this conditional distribution is badly chosen, right, and you are constantly rejecting samples, you'll just stick with this one sample all the time, which of course will not give you a very good representation of your posterior at all. So that's why it's important to choose a conditional distribution that actually allows us to transition quickly and draw as many different samples as possible. And I'll show you an algorithm that accomplishes that very, very well in a minute. But let me first help you visualize how Markov chain Monte Carlo actually works. So generally, we'll start out somewhere in space because we need to initialize the algorithm somehow, right? So we'll initialize it with a random sample. And then let's assume that this red line over here is our posterior, right? So our posterior happens to be this weird shape, kind of like almost rectangular, with a hole in the middle. So then we start out somewhere randomly in space. And what the Markov chain algorithm does for us, or Markov chain Monte Carlo algorithm does for us, is it moves us closer to the posterior. And then once it hits the posterior, it stays there. So then it starts moving around, and you can see that all of these samples are actually on the posterior. The important bit here is that it actually may take quite some time to hit the posterior. And obviously these first couple of samples are not representative of the posterior because, as you can see, they're not really lying in the posterior. So again, it is important to draw a lot of samples in that scenario because eventually, if we're drawing enough samples from the posterior, they'll just overwhelm these other couple of samples that are not part of the posterior, so that effectively we can neglect these first couple of samples, right? But in order for that to happen, obviously we need to draw enough samples from the posterior. So we need to stay inside the posterior for long enough and sample inside the posterior for long enough. So again, running the Markov chain Monte Carlo sampler for long enough is crucial at that point. So now let us look at a state-of-the-art method for Markov chain Monte Carlo. So actually, I presented Metropolis Hastings to you because it's like the classic thing to do. And there's some elements of that you'll even find in Hamiltonian Monte Carlo. But Hamiltonian Monte Carlo really is the state-of-the-art algorithm for sampling. And it makes sampling much, much more efficient by basically allowing for faster and wider transitions between samples. So two things. The algorithm is going to be faster as such. Why is it faster? Because it basically makes bigger jumps. So the distance between two adjacent samples is going to be large compared to Hamiltonian Monte Carlo, compared to Metropolis Hastings. So as I said before, worst case scenario would be that we never move, right? We just stick with this one sample. Well, what Hamiltonian Monte Carlo is going to do for us, it's going to not only move us away from the sample, but it's going to move us away from the sample very, very far. So that in the end, also, although it's still Markov chain Monte Carlo and samples are autocorrelated, that correlation may pretty much vanish because we're taking such large steps. And that also means that we're rejecting very, very few samples. It may still happen that we're rejecting samples, but by and large, we're going to reject very, very few samples. And I strongly encourage you to check out Michael Betancourt's Introduction to Hamiltonian Monte Carlo, where he really goes into a lot of depth and detail. And actually, the next couple of plots are from that paper. I'll somewhat gloss over the mathematical details here because it gets quite complicated, and just try to give you an intuition for how how Hamiltonian Monte Carlo works. So, as I said before, Hamiltonian Monte Carlo, or the goal of Hamiltonian Monte Carlo at least, is to take us further. So whereas with Metropolis Hastings, we saw all these dots that were scattered along the posterior, and they were very close to each other, what we're trying to do with Hamiltonian Monte Carlo is we're going to try to move very far. So instead of having adjacent samples being literally adjacent, we want to have them as far as possible apart from each other. And why? Well, we want to explore all areas of the posterior. We want to get a representative sample. The most efficient way to do that is to just move as far as we can, because thereby we'll ensure that we're in a completely different space of the posterior. And even if we're not drawing a whole lot of samples, say even if we're only drawing 100 samples, because we have explored so many areas of the posterior, And that'll actually help us get a better summary of what the posterior looks like. So it's called Hamiltonian Monte Carlo because it uses Hamiltonian dynamics. What are Hamiltonian dynamics? Well, Hamilton came up, or rather, Newton came up with the thermodynamic laws, and those were later on formalized as Hamiltonian dynamics. And Newton's second law, what does it state? Well, it states that energy can't evaporate, right? So whatever you do, whatever physical movement you do, whatever physical activity is happening, energy can help change the state of matter from one state to another. So think, for example, of water. If you cook it, so if you add energy, it'll turn into steam, right? So that's what's happening. But the overall amount of energy that's there never changes, right? So if we're thinking about a closed physical system, and that closed physical system being your kitchen, the overall energy in your system doesn't really change. And that's what we are going to exploit in Hamiltonian dynamics. So we're going to have Z as a position variable. And remember, Z is our latent variable that we're trying to do inference over. And we're going to have U called a momentum variable. So the position basically tells us where we are in the space. So think again of our posterior as a wiggly surface, right, with lots and lots of humps. And Z is the position variable, which basically tells us how high up these humps we are. And the humps are obviously just the density of the posterior. So if we are high up on a hump in the posterior, that means we're in a high probability region of the posterior. And that means that we have high position, right? Whereas if we're in a valley, we're in a low probability region of the posterior, then we have low position, right? And momentum basically gives us two things. It gives us direction and it gives us speed of travel. So basically say we're in a valley and we're surrounded by two humps, right? By two mountains. Now there's a decision that, or two decisions that we need to make. Which direction do we want to go? Do we want to go up the left hump or do we want to go up the right hump? And the second decision that we need to make is how fast do we want to go, right? And that's basically what the momentum variable tells us. So momentum is direction plus speed. And notice that momentum is crucial to actually get into onto these humps, because if I don't have enough momentum, basically if you think of a little ball that's rolling up a hill, if it doesn't have enough momentum, at some point it'll stop and it'll reverse and roll down that hill again, right? So if we actually want to get into high probability regions, we need some momentum, or sufficient momentum, in order to get up these high probability regions. So how is the Hamiltonian function made up? What is it made up of? Well, once we have the joint density as before, and that will basically, again, give us a measure for the height in our posterior. And notice that, again, we don't need the normalizer here, right? Because the normalizer doesn't really do anything for us. It doesn't change the shape of the posterior, just normalizes it, right? Whereas here, we just care about the height. And whether that height is scaled or not by the normalizer doesn't really interest us. So that's why we can actually neglect the normalizing constant p of x here. And then we have to define the momentum variable. And usually the momentum variable is chosen such that it depends on the position. Doesn't need to be, could be chosen independently. And in fact, it's often chosen to be standard Gaussian. So in that case, it might just be chosen independently of Z, right? So if we choose PUZ to be independent of Z, and then we could just assume it's a standard Gaussian. And again, for practical purposes, that's often done. Now you can optimize your momentum variable, but again, we're going to stay with the simplest variant of the algorithm, and we're just going to draw from a standard Gaussian here. Okay, then what's actually happening? So notice that we do not really care about the momentum variable. It is a useful tool, and it enables us to simulate Hamiltonian dynamics, but we're not interested in it. What we're interested in is the posterior, and in particular, drawing samples from the posterior. So we are interested in getting samples from Z. What Hamiltonian Monte Carlo does then is the following. So unfortunately here, we have P and Q on the axes, but because I took this from Michael Benancourt's paper, but really what it is P is our U and Q is our Z. So we want to move in Z space, right? That's what we're interested in. We want to generate a new sample from Z. And remember that the difficulty of moving in Z space lies exactly in defining a good proposal distribution that will get the next Z sample accepted, and at the same time moves a long way so that we don't have Z samples that are very close to each other and highly correlated, right? So how does Hamiltonian Monte Carlo achieve that? Well, at any given point Z, right, at any given position, we're going to sample a momentum variable, which means we're going to sample a direction to go in and the speed at which we're going, okay? And that's our U variable. So we're saying, so the technical term is we're lifting Z into UZ space, right? So Z space is one-dimensional. U space is also one-dimensional. UZ space is this whole thing here, it's this whole plane, and it's two-dimensional. So we're lifting Z into UZ space, and then using Hamiltonian dynamics, we travel in joint UZ space for a given period of time. And then we project that UZ sample, that joint UZ sample that we get down to Z space. And just as lifting simply means we are sampling randomly from U, projecting down to Z means we're just throwing away the sample of U at that point, and all we're left with is a new sample of Z. And because we're using Hamiltonian dynamics, and because U and Z together make up an energy function and energy stays constant, right? The probability that we get another sample Z that is in the posterior, although we have traveled very far in the posterior, is very high, which means the acceptance probability is also very high, right? So the whole trick here is really by moving through joint UZ space, we are able to generate a new sample that has very, very high probability of being accepted. And what we've achieved is that A, we have high acceptance rate, so our samples are actually different. And B, not only are they different, but they're also very far apart from each other, thereby reducing autocorrelation. Now let us look at how Hamiltonian Monte Carlo can be implemented. Just as with variational inference, although there's quite some heavy mathematics involved, the implementation is actually rather simple. So what we're going to do is at each point that we are advancing in UZ space, we're going to advance as follows. So we're going to first move half a step, or we're going to update U by half a step. Then we're going to update Z by one full step, and then we're going to do another half step of U. So instead of updating all variables jointly, as we did with variational inference, we're actually updating them one after the other. But instead of taking full updates for U, we're actually just going to take half updates for U at each point. And that has to do with just the convergence of the simulation of the Hamiltonian dynamics. But basically what I want you to note here is three things. First of all, this can be anywhere in any given step of the trajectory. So I told you initially that U gets sampled randomly, right? But it only gets sampled randomly once. We don't ever resample it. Or rather, we sample it when we want to generate the next Z sample. But while we are in one trajectory in UZ space, so while we haven't projected down to Z yet, while we're in this one trajectory in UZ space, we update U, but not by sampling, but rather deterministically by implementing these Hamiltonian dynamics. And then for each advance in U and Z, what we do is first we do a half update to U, full update to Z, and then another half update to U. And these updates are just defined by how Hamiltonian dynamics defines them. And in order to update U, we need to take derivatives with respect to Z, which again is going to be done for us by automatic differentiation. So even if we have a very complex model here, we don't really need to worry. Then Z is simply updated with the value of U. And again, then we update Z again with the gradient with respect to Z. Just notice that before we took the gradient with respect to the previous value of Z, and then the second time we take the gradient with respect to the current value of Z. And one more thing to note also is that we have epsilons here. These are not random samples, but rather they are, if you wish, our learning rate, or the rate at which we want the trajectory to move. So in particular, if epsilon is very large, then the steps that we're taking are going to be large too. And if epsilon is small, we're going to take smaller steps. And it's often preferable to take smaller steps. It means we'll have to take a couple more steps, but at least we'll get higher accuracy in the sample Z that we're producing, which again means we'll get a higher acceptance rate. So let me show you how this can be implemented in Python. So we have the step size epsilon, and then it's really just update y. So y is our u, update x, which is our z, and update y again, which is our u again. And that's already it. And how do we update y, or rather u? Well, it's exactly this. So we take the gradient with respect to the position variable. And this gradient here is just a black box function again, right? That's some automatic differentiation magic that is happening, and you don't really need to worry about that. And the update with respect to y is then the same thing, just that we're taking, sorry, the update with respect to z is the same thing, just that we're taking the gradient with respect to u. And you can see that all of this here can basically be automatized by exploiting automatic differentiation. So if you have the automatic differentiation routine for whichever model you're using, then the updates are very, very simple and very straightforward. Okay, further topics that you may want to look into when it comes to HMC is setting the step size, so the epsilon parameter for HMC, because setting it by hand can be a bit cumbersome, and there's actually ways to set it automatically. Moving away from HMC, or rather, let's stick with the topic of HMC. So another thing you may want to look at is the no U-turn sampler. So I gave you the very basic version of HMC that has its own problems. It still works pretty well, but it can be made even more efficient with something that is called the no U-turn sampler. So basically what it does is it avoids that the chain doubles back on itself. So in theory, say our posterior is a circle, right? Then if I take a very large step, it may happen that I still end up with highly correlated samples. And why? Well, because I went one time through the entire circle and ended up very close to my initial position. So what a no U-turn sampler does is it doesn't do any U-turn. So the moment it recognizes that the trajectory is doubling back on itself and in danger of hitting the starting point, it just stops the trajectory and takes the point that we're currently at as the new proposal for Z. Very interesting paper. I encourage you to look at that. More towards the general theme of sampling, something that is also worth checking out that I didn't talk about today is the Gibbs sampler. And why? Well, HMC requires differentiability of the variables, and it doesn't work very well for discrete variables because discrete variables are often not differentiable. So in that case, you may want to use the Gibbs sampler. So the Gibbs sampler is another, so different from Metropolis Hastings, different from Hamiltonian Monte Carlo, is yet another sampler that unfortunately is not very efficient, but works really well when you're dealing with discrete variables. Okay, let me finish up this section by talking about some applications. Now, all these applications can in principle use Hamiltonian Monte Carlo or variational inference, but I'm going to present two applications where sampling, not Hamiltonian Monte Carlo, but where sampling has been used. So one is the Netflix challenge. And this here looks very, very complex, but it was actually the winning model, I believe, and it's a Bayesian matrix factorization model. So what Netflix wanted to do is it wanted to predict ratings for movie customer pairs, which hadn't really occurred, right? Because the problem is that most customers haven't seen most movies, right? So each customer maybe has seen 100 movies, but Netflix has thousands in its library. So how can it predict the ratings for customers and movies that the customer hasn't seen? Why would it want to do that in the first place is the question, so that it could recommend movies to new customers, right? Or to existing customers also, but basically recommend new movies that the customer hadn't seen yet. So they would basically try to extrapolate what hypothetical rating the customer would give to any given movie. Okay, so the rating is what we're trying to predict. And the model basically has a movie embedding and a user embedding. And the rating then is the result of a matrix multiplication between the user matrix and the movie matrix. And each of these has its own hyperparameters and its own priors. And why? Well, again, because most customers don't actually watch a lot of movies, right? So it's really hard to find a customer representation, a customer embedding that represents that customer well. So if I just joined Netflix and I've only seen 3 movies, you don't really know what my taste is, right? And you don't really know how you should represent me in that matrix factorization framework. And then the priors help to get information about customers that haven't seen a lot of movies, or about new movies, for example, that a lot of customers haven't seen yet, by sharing information between existing customers. So this basically says, if I am a new user, I haven't seen a whole lot of movies, Netflix doesn't have a whole lot of information about me, then they're just going to treat me very, very similarly to the average customer, right? So if you don't know anything about me, just assume my taste is that of the average person. That's basically what it's saying. And then incrementally, as I watch more movies and as I make my preferences known to Netflix, this customer embedding for me can then get updated accordingly, and can, if I'm not like the average customer, can move away from the average customer embedding. So that's basically the idea of the model, and their sampling techniques were used in order to do inference on the models and in order to infer the distributions over customer representations and over movie representations. Another very, very famous example where actually both variational inference and sampling methods have been used is topic modeling. So topic modeling is basically used for ordering text and also for genome sequencing, and basically any task where you have a lot of data but not a lot of structure. And you want to organize that data somehow so that at least you have some structure in your data, right? So basically, if I'm giving you a random genome or if I'm giving you a random library, your task is to somehow organize these thematically. And topic modeling achieves this as follows. It basically categorizes words according to their topic, where the topic might be something like arts or budgets or children or education, something along those lines, right? And once I know which topic a word is likely to belong to, I can then extrapolate to texts, right? Because texts are made up of words. And if a text contains lots and lots of words from, say, the art section, I can then categorize this text as being about arts. Now, obviously, there is not all texts only belong to one category, right? So, for example, I might write an article about the economics of the arts business, which would mean that probably there'd be lots of arts words in there, but also lots of budget words. And that's the cool thing about topic models, because they're probabilistic, they allow you to make soft clustering, so to speak, right? So a text might be 60% in the art section, but at the same time, 40% in the budget section, exactly because it is a text about the business of arts. So yeah, these topic models have been hugely successful, tremendously successful in all kinds of applications. Another example just comes to mind is social media analysis, right? You're some company and people are tweeting you, and you're literally getting thousands of tweets every day. So there's no way you're going to have your social media consultant look through all of them, but rather you can run automatic models, topic models being one class of models that you could apply, and categorize these tweets. For example, you might want to use is if they're positive or negative, if there's feedback that may help you improve. So yeah, these models are tremendously useful. And again, traditionally, variational inference and sampling methods have been used. And there was kind of this flip-flop. So it's interesting. It actually tells you about the development in research on inference methods, because initially, variational inference was used for topic models. Then for a long time, maybe 5, 6, 7 years, it was sampling methods that dominated topic modeling, just because they gave better results. They were more accurate. And at the same time, the corpora that were used, so the text collections, weren't super, super large. So they were at a scale where you could still use sampling methods and get really, really good results. And these days, we are back to variational inference again. And why? Well, because the corpora have just become extremely large, right? If you want to do this on all of Wikipedia or even larger text collections, then sampling is just not going to scale. And that's why people have reverted back to variational inference, accepting a potential sacrifice in accuracy, but just needing to use variational inference because it is that much more efficient, right? And there it's nice because you see the history of algorithmic development, but on the other hand, it also gives you an intuition for when to use sampling or variational inference. So variational inference, when you have huge text collections, go for variational inference. If you have smaller text collections and you can afford to wait a little longer and want really, really accurate results, then you're much better off using sampling methods. All right, at this point, it's my pleasure to thank you for attending. I hope you have lots of questions now that you can ask us afterwards. But let me first summarize what we've learned today. So first, we have learned about probabilistic graphical models, and they enable a couple of things. They enable you to specify the structure of the problem. So any real world knowledge that you have about how the problem is organized or how the variables involved in a problem relate can be used in model building. And they allow for uncertainty estimation. So instead of saying, as I said before, right, a text belongs 100% to the arts category. No, it may belong to the arts category to some degree. It may belong to the budget category to some degree, right? And that uncertainty estimation is crucial. And in particular, you may be able to average over uncertainty. So that's very interesting when you're looking at posterior uncertainty in particular. If we think back to the variational autoencode example and the phases, right? Yes, you can draw particular phases and particular realization of phases, but maybe you also want to ask the question, what does the average phase look like? And in that case, you can just average over all latent representation and kind of get like the average phase that's somehow representative of the input data, of the input images you've seen. Probabilistic graphical models allow you to reason about parameters. So again, that goes back to the Netflix example where our parameters were the embeddings for customers and movies. And instead of just choosing fixed embeddings, we can actually have uncertainty about the embeddings themselves, and we can reason about them. And in particular, we can say something along the lines of, if I have very little information for this customer, I may not be able to produce a good embedding. So rather, I'll make his embedding very, very close to the average embedding. And then finally, another application of probabilistic graphical models is causal inference, which unfortunately we didn't have time to cover today, but that is basically simulating experiments, right? Where usually you would do a drug trial on a control group and a treatment group. You may not always be able to do that, right? So for example, if you look at experiments with potentially fatal outcomes, you can, for ethical reasons, just not afford to actually have a treatment group because, well, chances are the treatment is going to kill people. So what you're going to do instead is you're going to look at observational data. So historical data where people by accident or by force of nature have either gotten a treatment or not gotten a treatment, and basically try to make draw the same inferences that you would with experiment, try to draw the same inferences from observational data. And that is something that you need probabilistic graphical models for as well. Then in the second half of this tutorial, we've focused on inference and learning. And we've seen that inference in general is harder for probabilistic models than just simply maximum likelihood learning. That's kind of the bad news. The good news is that there are some general purpose algorithms that work very well for most problems. And these are automatic differentiation, variational inference, and Hamiltonian Monte Carlo. You have seen those and can probably by now implement them yourself just by going through the slides again and basically copying and pasting the lines of code. But there's also many, many implementations around. So your time is probably more wisely spent on actually developing models and just using the packages that provide implementations of ADVI and Hamiltonian Monte Carlo. There's yet another piece of good news, namely that probabilistic inference is an active topic, very active topic of research. So once you start getting into that a little more, if you're interested, you'll see that there are lots and lots of improvements on these algorithms, and that by really understanding these algorithms and digging a little deeper, you'll get massive speedups and massive performance improvements when you're using approximate inference algorithms. All right, so that's it from my side. Again, thanks a lot for attending. I hope you got something out of it. And if you have any questions, then we'll be around, and please feel free to ask your questions. Thanks a lot and have a good day. Bye.